Okay, so now we're going to look at a different kind of kinematic problem. It's just like some of the other ones we've been looking at, but this is what I would call a two-phase kinematic problems. It's basically like two problems just stapled together is what happens. And I think you'll figure out what I'm talking about in just a second. So, you are driving a car, and it's traveling at a constant velocity of 25 meters per second. I think I used that for the last example. I don't know why I'm obsessed with 25. But anyway, when you see a child suddenly run out into the road, and it takes about 0.45 seconds for you to react and apply the brakes. As a result, the car slows with a steady acceleration of 8.5 meters per second squared and comes to a stop. What is the total distance? The total distance that the car moves before it stops. Okay, well that's the problem. Now, why do I call this a two-phase kinematic problem? Well, if you notice, there's really two things going on. This car, gotta draw a car. There it is. Doesn't look very sporty. I'll give it a little spoiler there. Beautiful. So this thing is zooming along, and there's sort of two different phases to what's going on, right? The first little phase is reacting. We have this person who is, driving along, and it takes 0.45 seconds just for you to put your foot on the brake. So this car's not slowing down, it's not doing anything. Ultimately, over here, it'll come to a stop, but that's, it'll come to a stop, but that's because this is the part where you're braking. So here is just sort of a reacting phase, you can call it, and then this would be a braking phase. Phase makes it sound complicated. It's not really that complicated. It just means that you have one kind of acceleration here. When you're reacting, you're traveling along at 25 meters per second. You haven't hit your brake. Your acceleration here is actually 0 meters per second squared. You're just cruising, right? Constant velocity. Braking is different. You're going to be slowing down. So here, if I were to draw this, here's a little motion diagram. Little velocity vectors. The velocity is just staying. The initial velocity equals the final velocity, which is this 25 meters per second. This is different. This is different. We got a situation where we have an acceleration this way, right? Because you're braking. So we can write that as 8.5 meters per second squared. That's what they tell us it is. Not only that, since it's going this way and your car is going this way, generally we would make that, here I'll draw it, make sure I get the right color. When you choose an orientation, a lot of people like to choose right to be positive. I happen to draw this picture to the right, so we'll go with that. So that means that this acceleration is actually negative. It's in the opposite direction to your velocity. So what happens to your velocity as this acceleration is being applied? Well, the minute you start braking, this velocity vector is getting smaller, 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 and smaller, until you just stop, until you have a final velocity of 0, right? That's the idea. So, is the kid safe? I don't know. This is very exciting. So, let's figure out what's going on with this. So, it's asking us to figure out the total distance that the car moves. That's from this point to this point, x total. But hopefully you can see that x total is a combination of how far it moves in this first part, phase 1, and how far it moves in the second part, phase 2. Now what's nice about this is that 0 acceleration is a constant. Negative 8.5 meters per second squared is a constant. So that means for each of these sections I can use, that's right, the kinematic equations. I'll write them out over here if I can remember them. I think I can remember them. Look, I'm doing it while talking. That's amazing. It's because you do this for years. So anyway, there's this lonely little, oops, that's supposed to be squared. The lonely third one, which I think is kind of the underdog. Really helpful. Okay, the three kinematic equations, that's what we're going to be applying to this situation. Alright, so let's do it. Yikes, where'd the problem go? There you are. Don't run away. Okay, so what I'm going to do is I'm going to calculate this first. How far does he move when he's just reacting? And then I'm going to calculate that, and then we'll add it together. So, in part 1 of this problem, what do we know? Well, we know that this thing has initial velocity and a final velocity of 25 meters per second. Because they're just stunned. They haven't hit the brake yet. and we know this car is traveling this way for 0.45 seconds, and I can also write that there's 0 acceleration. That's how I know that this is true. And we want to know what is my final displacement. How far do I go? All right. Well, I'm given a lot of information, including t. So I'm thinking if in distance, time, distance, and velocity, I think this second equation is what we want to try. Let's give that a shot. So x final equals x initial plus VIT plus 1/2 AT squared. And let's see what happens. Well, if I call my initial position 0, which makes a lot of sense, that just goes away. My acceleration is 0. That means this part goes away because I just multiply by 0. So all I'm left with is my final distance equals my initial velocity, which is 25 meters per second, times how long I'm going that way, which is 0.45 seconds. So this is telling me that for phase 1, my displacement is, if you multiply that out, you'll find it's 11 meters. Is that my answer? No. It's part of my answer. I got to get this x2 as well. So let's get a little more screen space for that. So in the second part, well, let's think about this. Okay, so this part 2 is picking up right where part 1 left off, right? So the question is, what is my initial velocity for part 2? Well, he hadn't started braking yet, so his initial velocity is 25 meters per second, exactly how fast he was going in phase 1. Final velocity, well, tells us we come to a stop. Stop is 0 meters per second. Acceleration isn't 0 anymore. It's going to be this negative 8.5 meters per second squared, and they're asking me, how far do you go? That's what we're wondering, and then we're going to combine it. Let's see what happens. Okay, how far do I go? Well, which kinematic equation do I want to use? That's kind of the real question. I have information on velocity and acceleration. I don't have anything on time. And wouldn't you know it, here's the underdog. Let's use this third guy. Let's see what he can tell us. I think it's got distance in it, which is what we're looking for. Let's do it. Final velocity squared equals initial velocity squared plus 2 times acceleration. Final minus initial position. Alrighty. My final velocity is 0. My initial velocity is 25 squared. My acceleration is negative. Yes, you want the negative sign there. Negative 8.5. And then this, well, once again, if xi is 0, this just turns into x sub f. Well, let's see. We got to solve. Now it's just algebra, but let's solve for this. So 0 squared is just 0. 25 squared is 625, but I got to subtract that from both sides, so I'll have a negative 625 on this side. And then this, when I multiply this out, that's negative 17 x sub f. And so we got a negative divided by a negative, so that gives us a positive, and our positive displacement is 37 meters. There it is. That is for part 2. So what I really need to think about is, what is my total displacement? That's what it was asking me. Well, 11 meters for the first part, 37 meters for the second part. So I end up with a total displacement of 48 meters for this whole thing. Hopefully the kid is farther than that, or he got flattened. That's a sad story. I'm going to just pretend that he's fine. He's fine. Don't worry about it. He's good. So anyway, review this as you need to, and maybe walk through this step by step, and you can even try it on your own with different numbers.